Uh-oh. Okay. So during the break, there was a question that reminded me of something that we didn't do in the cross-Claisen reaction. It's not very new. It's a variation, though, on it that I think is worth mentioning briefly. The thing that really makes the Claisen a Claisen, I got my old guy glasses out here because I'm looking at the textbook, I'm sorry, is the fact that the electrophile is an ester that has a leaving group on it. One example of the Claisen is to use a ketone enolate as your nucleophile, and then to use the ester as an electrophile. The reason I mention this is because the product you will get from this looks like a Claisen product, but not completely. So I told you before that a beta ketoester is a classic example of a Claisen product. Here is a ketone, and then here is an ester. And I'm just choosing, the process works best, your text says, when your ester has no alpha protons, because you don't want potential self-Claisen products to compete with the desired cross-Claisen product. So as an example, if you were to use a base, I need just a little bit more space on the side here. You would form an enolate first. I won't show you that proton transfer. I'll just write deprotonate, which was probably slower than drawing the proton transfer mechanism. Here's the alpha carbon. That enolate attacks the carbonyl carbon to give a tetrahedral intermediate. I will assume you can draw the mechanism from there on. The product here has us make this bond between the alpha carbon of the enolate and what used to be the carbonyl carbon of the ester. So I'll highlight in orange the portion of the molecule that used to be the ester, and in purple I'll highlight the portion of the molecule that was our enolate. Notice that here's the carbonyl carbon of what used to be the enolate, here's the alpha carbon, and then you have a beta carbonyl group. This product is a beta diketone, not a beta ketoester, but you can see mechanistically this is totally a Claisen reaction because your electrophile is an ester. So when you're doing problems of this nature, if you see a beta diketone and you know you need to make one of the bonds between the alpha carbon and one of the carbonyl carbons, choose as your ester, if you have a choice, choose as your ester one that lacks alpha protons. Okay, so that's just something that I failed to pick up a little bit earlier. Sorry about that. Now, we were going to jump into the Robinson annulation where your product is a cyclohexenone ring. So let's show you how this works. In the Michael reaction first, of course, we're going to have a carbonyl compound act as an enolate and attack an alpha beta unsaturated carbonyl compound. So actually what I will do, instead of starting with the mechanism, I just want to draw the starting materials for you. And then here's our alpha beta unsaturated carbonyl compound. This happens to be a beta diketone. You don't have to use those as nucleophiles in the Michael reaction, or rather in this Robinson annulation reaction, but that's just what the example is that I'm taking from your text at this point. This is going to be your enolate nucleophile in the first step. Your products, you ready for the horror? You guys remember that moment in Star Wars Episode 1, The Phantom Menace, when Darth Sidious instructs Newt Gunray, the Viceroy of the Trade Federation, that his apprentice Darth Maul will be joining them. And then the other guy says to Newt Gunray, now there are 2 of them. We started with 1 6-membered ring, now there are 2 of them. I think the payoff on that reference was not worth the setup. Yikes, okay. So how do we do this? Actually, it's good to know where you need to end up, and it's also good in a Robinson annulation type of reaction to have a good sense for what portions of the starting material end up in what portions of the product. So these carbons in blue are here in the starting material, in the product. These carbons in pink are here in the product. And with a squiggly line, here are the bonds that you make. In other words, we make in this reaction 2 carbon-carbon sigma bonds and 1 carbon-carbon pi bond. All right. These bonds here we make via the intramolecular aldol reaction. Intramolecular tells you that that's got to happen second, because we got to first get these 2 portions to be part of the same molecule. This bond up top we make via the Michael reaction. And your text sort of takes you through and points out how, okay, if you have a cyclohexene ring product and you draw it in just this way, with the double bond on the bottom and the ketone angle down towards your lower left, then you just slice it down the middle here. This portion used to be your enolate nucleophile, and this portion used to be your alpha beta unsaturated ketone. I can basically guarantee you that when I put options on multiple choice tests, I will not draw them as nicely as this. They'll be drawn in, just spin it around, flip it over. You'll have to be able to manipulate molecules in 3D to be able to see that. All right, let's go through the mechanism. As I said, this is the longest mechanism you'll have to do probably in the class. So to do the Michael reaction, we first need to convert, and actually to do this, all you need is a base. So it's a fairly simple reaction in terms of reagents. You've got your starting materials and then a base, frequently hydroxide. So first, we're going to make the enolate. It's convenient that we chose a beta diketone as one of our starting materials, because this alpha proton in pink is the most acidic alpha proton present. So we're just going to have OH minus remove that alpha proton. It can do so quantitatively, because the pKa of that proton, if you go look it up, ends up being around 9. So totally fine for OH minus to remove that proton to give us this enolate. Then we're going to do the Michael reaction, which, as you know, involves the pink alpha carbon now of my enolate attacking the blue beta proton of my alpha beta unsaturated carbonyl compound. we're going to do just exactly what we did before for the Michael reaction. We're going to take the electrons from the pi bond between alpha and beta carbons and move them onto the alpha carbon. Of course, we could also have pushed arrows to get to the other resonance structure of the resulting enolate. Here's the negative charge on the alpha carbon. Here in red is the new sigma bond that we made between beta carbon of my alpha beta unsaturated carbonyl compound and the pink alpha carbon of my enolate. All right. So there we're actually almost done with the Michael reaction. Now we simply pick up a proton from water. And that concludes the Michael reaction. And I'll continue to highlight things, hoping that it's helpful. All right? And maybe we'll continue to highlight in red the bond that we made. Again, it's useful to label your carbons so you can have an idea of where you've been. All right, so that's the Michael product. How can you tell it's a Michael product? Well, we could number the carbons 1, 2, 3, 4, 5, a 1,5 dicarbonyl. And then the other thing we could do is notice that the pink alpha carbon from my enolate is now at the gamma position relative to the blue carbonyl carbon. All right, questions about that? Not too bad. All right, so now let's look at the lower hemisphere of our molecule. The second stage of the Robinson annulation is an intramolecular aldol reaction. And that's going to involve the pink carbonyl carbon and then the other alpha carbon, we'll call it alpha prime, of the blue portion of the molecule. You can see that they're close to each other. In fact, 1, 2, 3, 4, 5, 6 atoms away from each other. If we make the enolate here, it could attack this carbonyl in an aldol reaction. Go ahead.
Is choosing that alpha proton there, that's just because we already need another ring, that just to minimize ring strain?
So why would we choose this alpha proton instead of this one? Right, if we choose this one, that makes a 1, 2, 3, 4 membered ring, and that's not as stable. This is an equilibrium process. At least the intramolecular aldol is, and so we are going to make the most stable 6-membered ring. Yep. Yeah, go ahead.
What if you chose the hydrogen that's right next to the carbonyl carbon?
This one?
Yeah.
Okay. If we chose this one, that would give us a 1, 2, 3, 4, 5, 6-membered ring. But there would be, if you look at it, 1, 2, 3, 4, 5, 6, that would create a kind of strained bicyclic system where, I don't know that I can do this on the fly, it would sort of look like this and likely is not as stable as the other option. I don't have a fantastic answer for that. We could draw it out. Your text doesn't show it as an option. My guess is that that pathway isn't preferred because it's not as stable. Yeah?
Why choose one ketone over the other if you use the same one that we were just about to use, the alpha hydrogen on
This one?
and then use the other ketone?
Yeah, notice actually that these two ketones are identical by symmetry. So we'll get the same product whether we go one versus the other. Yep. Right. If you look at our product, though, our product is chiral. It has a stereocenter here. We're going to get both enantiomers, and probably you get those both enantiomers from attacking one ketone versus the other. Okay. Other questions? Yeah.
What if you didn't have two ketones? What if one of them was an ester? Is there a way to do like a Claisen reaction with this, or does it
Well, that's
have to be
interesting. So using a beta diester, could the next phase of the reaction be a Claisen? That makes a lot of sense to me. It's not presented in your text. It probably exists because that seems like a totally reasonable thing to do.
Okay, and then in that situation, would there be a preferential one to attack if there was one ketone, one ester? Would it be
Oh
better?
wow! I mean, I don't think so. I think you're right to be asking about it, and I don't want to go too far down the hypothetical rabbit hole here. But I think the question that's being asked is, if you're at this stage, could you do an intramolecular crossed Claisen reaction, and would that be preferred relative to an intramolecular aldol reaction? I don't know. I think probably the crossed Claisen would be preferred because there's a thermodynamic sink that you can fall into from the resulting beta keto ester, but we don't need to go down that pathway too much. I don't, in the years that I have taught that question is actually, I've never actually had that question, so congratulations, good question. But it's not in the text, and so I think it's a reasonable thing to do. I think probably we won't worry about it.
Okay.
Disappointing, but yeah. Okay, so we've paused here at the stage of the Michael product to consider what could happen next. And you're noticing that this is a carefully curated example because there's not a lot of other things that could happen. What I'm saying is we don't have to worry about which of the two carbonyl carbons this alpha, blue alpha prime is going to attack because they're identical. We're also not worried about what we might call pink alpha prime attacking the blue carbonyl carbon. In part, even though we haven't considered that because that doesn't lead to the most stable product. And we haven't totally illustrated that. You may need to just accept that on faith at this point. So that's the Michael product. Now let's consider how we do the intramolecular aldol. And this part's just going to be review because you've seen an intramolecular aldol reaction before. And to review another question that came up, why are we going to deprotonate the blue alpha proton? They're both blue, sorry. Why are we going to deprotonate alpha prime instead of alpha? Because deprotonating alpha prime gives us the more stable 6-membered ring as opposed to a 4-membered ring that you would get by removing just regular alpha. So let's take the base, let's remove the alpha proton to make the enolate. You could draw the arrows in the way I've just done, or you could draw the arrows in such a way as to get the other resonance structure of the enolate. I don't totally love that drawing, but I guess we'll live with it. All right. So we'll have this carbon attack the carbonyl carbon in an aldol reaction. That makes the second sigma bond. So here's the first, here's the second. Here's what used to be the carbonyl carbon that was attacked. It's now a tetrahedral intermediate. Here's alpha prime that did the attacking. Here are the alpha and the beta carbons, the alpha carbon that attacked in the Michael reaction, and we'll continue to highlight things as we've done previously. Okay. So that's the carbon-carbon bond forming step of the aldol reaction. What we're going to do from here on out is just we're going to protonate the negatively charged oxygen. Then we're going to do and that will give us our beta hydroxy carbonyl compound that's an aldol product. Then we'll do that dehydration reaction via the E1CB mechanism to get us our final cyclohexenone product. Look at where we're going to end up versus where we are at now. We need to get rid of that beta hydroxy group. Okay? So to do that, we protonate on the negatively charged oxygen of the tetrahedral intermediate. Okay. And now we need to do the dehydration reaction. Remember that this reaction happens, or the elimination reaction happens stepwise via an E1CB mechanism. We deprotonate the alpha carbon to make the enolate, and then, and only then, can we kick off the OH group as a leaving group, and that makes the desired cyclohexenone product shown here. All right, questions about the intramolecular aldol? Go ahead.
Can you remind me why it's reasonable that we kick off the OH?
Why can we kick off the OH? A negatively charged carbons are good enough kicker offer for OH minus to be a good leaving group. But the OH minus being a poor leaving group is why this mechanism of dehydration is E1CB rather than E2. It's why we don't pull the proton, kick off, and OH leaves in the same step. Okay, good. What else? Okay. So that's sort of the worst. Of course, with any reaction, you can do things in a predict the products or retrosynthetically sort of think backwards. And actually, I just saw something in the text that addresses a question that came up earlier. So maybe we'll do this as an example. Someone asked earlier about what if your thing that you're using as your nucleophile instead of being a diketone was a diester. And I'm just going to show you what the book shows without, and then we'll talk about an alternative possibility, and apparently it's not something to worry about. So here is the molecule that's going to be your enolate. You can tell because it's the other one that's the alpha beta unsaturated carbonyl compound. All right, so predict the products. You don't have to draw the mechanism. As you're starting out, you may wish to draw the mechanism in order to help you predict the products. as you get better at this, you won't necessarily need the mechanism. It may help you at this stage to draw the starting materials in the same orientation that we used here. You don't have to, but it may help. It may also not. I'm also going to recommend that at an early stage you think about that you maybe draw the intermediate Michael edition product to help you figure out what's going to happen. So without doing the mechanism, your text says we're using as base ETO minus, and that means we're going to remove this proton to form the enolate. So this is our nucleophile. So let's draw the product that would form the Michael addition product. And as I said, maybe it would help to redraw the alpha beta unsaturated carbonyl compound and the enolate in such an orientation that it sort of looks similar to what we've seen before. All right, that's the same molecule, right? And then I'm going to abbreviate the ester like this. All right, so the Michael addition product is going to look like this. And I'll choose blue to highlight. We can even label carbons. In red is the new bond we made in the Michael reaction. And that red bond is between the pink alpha carbon and the blue beta carbon. So now I can draw the four-membered ring with a carbonyl here. And then the ester there. All right, so that's the Michael addition product. Questions about how we got there? All right, so I think the question you asked was here now, if we look at carbon alpha prime and we think about the intramolecular aldol reaction and deprotonating that, and then which does it attack? We're seeing that I could attack the carbonyl carbon to do an aldol, but then I think you're pointing out that I have this ester carbon up there, and why don't I do the Claisen reaction? Why don't I make a 1, 2, 3, 4, 5, 6-membered ring there? I don't have an answer for that, actually. Your text doesn't show that as an option, or even explain why it's that way. And so, yeah, I agree that that's unsatisfying. And what that means is you're relying on memorization to figure out what's going to happen here, and that may be the best that we can do. So in the second step of the Robinson annulation, the intramolecular aldol step, you need to find the pink ketone, meaning you find the portion of the molecule that was your nucleophile in the Michael reaction, and you find the ketone portion, and that's going to be the one that's attacked. That's presented here without justification. I haven't thought it through well enough to give you a good answer, so I apologize for that. Go ahead.
So if we were to attack the other carbonyl, it would maintain the two rings that are like attached to each other, the two rings that will be attached but by one carbon next to each other.
Okay.
change anything?
It might, I mean,
Like, is the product of the Robinson always two rings connected to the
is the product of the Robinson annulation always two rings with two carbons shared between them? It honestly depends on what your nucleophile is. If this nucleophile already has a ring, then yes. I mean, we could totally consider and draw the products that would form from having alpha prime attack the ester carbon. What you're noticing, some of you are noticing, is that the six-membered ring that would involve 1, 2, 3, 4, 5, 6 carbons would necessarily be linked to the five-membered ring through a linkage that looks like that. I don't want to go down that rabbit hole because I'm not sure that it would lead anywhere particularly fun. Other than to say that this type of connection, two rings sharing a single atom, is called a spiro connection. The spiro compounds are known, so I don't have a really good reason why we should dismiss that. My hand-wavy explanation must be, well, if it doesn't happen, it must not be the most stable option. But that's just another way of saying memorize, find the pink ketone. So, yeah, great questions, and I'm sorry I don't have a good answer for you there. So, the product after the the intramolecular aldol step of our reaction is going to be to make a new bond between blue alpha prime and pink carbonyl. That's going to make the six-membered ring, and I'm going to jump ahead past the tetrahedral intermediate and past the beta hydroxy ketone to the final Robinson annulation product, noticing that blue alpha prime also had a methyl group on it, and then I'm going to fill in everything else. And that's my Robinson annulation product. Okay. So I want you to practice that in a predict the product sense. It's a lot to take in, but the more you practice, the easier it is to see. I think at this point, going through more examples together is actually not going to help you. You need to do it on your own and make sure that you can do it. Let's talk about retrosynthesis. And because this is a favorite multiple choice question on the exam. Here is a Robinson annulation product. Which of the following were starting materials? And then options A through G or J, or however many options I have, 10 I think max. It's enough that you will waste time if you go through and try to evaluate all the options individually. Instead, you ought to just figure out how to do this yourself by hand as though it were a free response test, and then pick the answers that you obtain out of the list of options. So let's think about what were the starting materials for the following Robinson annulation product. And I'm not going to draw it in a way that's easy to see. Now there are 3. Don't worry about it. You only make 1 in the Robinson annulation, which means a lot of the rings you can probably ignore. Ooh. Is that a Robinson annulation product? Trick question. What's missing? It's got to be a cyclohexenone. So if you get, I'm going to proofread the test so I don't do this, but if you're in there and I say, which of the following are the starting materials for making this molecule via the Robinson annulation, and the product shown doesn't have a cyclohexenone ring, then you go ahead and fill in all the answers or none of the answers or whatever answer you want, because that's a botched question and you're going to get free points, all right? Unless none of the above. I suppose I could do that. Sorry, we're unleashing the horror. Now it's a Robinson annulation product. Okay? Now it's a cyclohexenone ring. It's not drawn for you in a way that makes it similar to what you've seen before. But actually, from a retrosynthetic point of view, it's not as bad as you think. The first thing you want to do in thinking backwards through the Robinson annulation is to find the cyclohexenone ring, which we are going to highlight in orange. That's the portion of the molecule that we made. Then highlight the pi and sigma bonds, the double bond, and remember that that was made via the intramolecular aldol. Now you can start to put things together. This carbon, the alpha carbon, used to be blue alpha prime, and the other carbon, because this bond was made via an intramolecular aldol, this must used to have been the pink carbonyl carbon. Okay? Then you're going to identify the blue carbonyl carbon, regular alpha, and beta. Once you get to beta, highlight the next bond, because that's the bond you made via the Michael reaction. Meaning that the other atom is pink alpha. Now we're almost done. It's literally almost done. We don't need to think too much more about how to do this. The red squiggly lines indicate the bonds that we made. So let's split the pieces apart. The blue portion now is my alpha beta unsaturated carbonyl. Continue to label the atoms. And then what about the pink portion? Sorry. The two things that were involved in the reaction were the pink carbonyl carbon. Since this was a carbonyl carbon, it needs to have had a carbon-oxygen double bond on it. The alpha carbon, which is still going to have the methyl group. And then if it was the electrophile in the Michael reaction, it would have been the enolate. So there would have needed to have been an alpha proton there. And then everything else about the molecule is exactly unchanged. Just draw it as is. Okay? Questions about that? Okay? Fine. Now you do one. This is 18.29a. All right. Take a couple of minutes. I want you to actually draw this on paper. Don't just sit there waiting for me to do this for you. Imagine that you're in an exam. I will, if we can sniff loudly occasionally and somebody can crinkle something, we can do simulated exam. If somebody could take out their model set and drop it, or, yeah, popping of bonds in a model set, good. And if you're done and are bored, you can start contributing to the exam simulation conditions by making distracting noises. Does that bother anybody? And for some of you at this stage, it may actually help if you redraw the molecule like this. Okay, what do you got? Let's just, for the sake of our discussion, I'm going to number the atoms 1, 2, 3, 4, 5, and 6. You can tell me, 1, 2, 3, 4, 5, and 6. Okay, which atoms were part of my alpha beta unsaturated carbonyl compound? I'll label them in blue. Somebody's saying 5, okay.
3, 4, 5, 6.
You want 3, 4, 5, and 6. Okay, and then that must mean 1 and 2 from that ring were part of my enolate to begin with. That means these two bonds in red were made in the intramolecular aldol reaction. That means this bond in red was made via the Michael reaction. So your starting materials should have been this and this. Got it? Yay! Okay. All right, well that's honestly all I had planned for today. Go ahead.
Is there anything stopping you from switching the cis trans double bond because you did the rings the other way?
There was a question, is there anything stopping you from switching the cis-trans double bond because you did the rings the other way? What are we talking about? Stereochemistry cis-trans? I'm missing that, sorry.
No. If you switch which one is the enolate and which one had
Oh,
the beta unsaturated, can you also form it that way?
I think a question is if I had used this and then this, would I have gotten the same thing? That's an interesting question, and I'm not sure. But we could do that. Those starting materials would lead to this Robinson annulation product. Yeah, that would put the methyl group in the wrong place. Okay, good. Other questions? All right, well, I don't know when in the history of 352 in the spring term have we ever finished like 10 minutes early and then just got home. If you insist on getting your money's worth, I will stand here until 9:50 and you can ask whatever questions. So let's just be done for the day and I will see you Monday.